proof from the book. And there are a lot of interesting stuff he introduced in mathematics and remained in very important positions, including the president of German Mathematical Society for a time, and he has been a member of the European Research Council, and also included in the American Mathematical Fellow of the American Mathematical Society, and won various prestigious awards in mathematics, including Steel Prize. Now he is going to discuss something very exciting, I would say, cannons at Sparrow, cutting polygons, and what that could lead to. So let us welcome Professor Ziegler. Professor Ziegler, you are on now. Welcome to your seminar, to John Conway seminar series.
Well, thank you very much. It's wonderful to be here. It's wonderful to have the opportunity to present this story, which I think is an exciting story. So thank you very much for the invitation. And of course, it's due to the COVID crisis and all the new forms of communication we are testing that way that makes it possible to be here and present mathematics somehow across the globe. So in that sense, thank you very much for the invitation. The story I want to present, I'll find my slides for. They are here. Although this is not the first slide, so I'll have to somehow try and see how I can get there. This is sort of the first slide. So the story I call Cannons at Sparrows, because you will see, shooting with cannons at sparrows is an expression in German, which I think also works in English, which means that you're using a huge machine to move across things. One problem I have is that somehow this thing is trying to forward my slides all the time, and I'll try and somehow stop it from that. But that's another effect in life, not only that people work with cannons at sparrows, but also that machines try and do things to us. And I will have to somehow try either Acrobat or Zoom to not forward my slides all the time. Anyway, so this is a story from mathematics, and the nice thing is that that it doesn't really belong to a certain part of mathematics, but we will really cross across fields. I will start with a little problem, which is what I will call the sparrow, and then we go on and see where this leads us. So the plan for this afternoon is to start with the little sparrow and then to show you the cannons, talk about some details. I will do a little picture show because that shows us somehow, sorry, I'm still suffering from Acrobat is forwarding my slides all the time. Anyway, so this is the plan, and I will show you the queen who shows up in the story, and we'll get a happy end. So I hope that that's a good plan for the lecture, and if yes, we will proceed that way. If you have questions and comments on the way, perhaps either open your mic and ask, or try and send a message on the chat, and I'll be happy to answer, not only at the end, but also in between if you interrupt me. So here comes the sparrow. So the sparrow is a little problem that was asked by a mathematician from India, Nandakumar, who I haven't met, but I exchanged messages from him. And on this blog entry in September 2006, so this is 15 years ago nearly, he asked the following problem, which is a problem which is a joint problem with Ramana Rao, a friend of his. he asked if you have a convex shape and a positive integer n, is there some way to partition the shape into n convex pieces so that all pieces have the same area and the same perimeter? So that's the problem. At the end of the blog entry, where you see that he's really an early morning worker, because this is morning at 7 in the morning, he said he couldn't find any result on this. Of course, you can cut everything into the same area and perhaps the same outer boundary. I'm sorry, this is skipping slides again and again. I'll try and keep it. And one observation he makes, if you do this type of cutting, it's not clear in the end which precise perimeter each piece should have. So they should have the same area and the same perimeter. Okay. Perhaps let me try it, because this is driving me crazy, to stop this and try just a different tool, namely no, this is not Acrobat, but Preview, and let's see whether that also manages to drive me crazy. Sorry about that. So this is this problem by Nandakumar, and to illustrate the problem, so perhaps I should say that a few years later, so we were 2006, now we are 2008, there's a first paper by Nandakumar and Ramana Rao, where they report that that they can solve the problem for n equals 2. And they give some arguments why it should be true for n equals 3. And in later versions of this paper, which were also published, they then finally somehow prove the problem for n a power of 2. But we will get there, and we will get further than that. Now, let's get started. N equals 2, this is a square. We are supposed to cut this into 2 pieces of equal area and equal perimeter. Now, this is rather easy. We could just use this cut, or actually any cut through the center will cut this into 2 pieces which are actually congruent. So this is much too easy with a square. So let's use something slightly more complicated. If we take a triangle, we're supposed to cut this into 2 pieces of equal area. You can always do that with a central line, but then the pieces will not have the same perimeter. And you could try and rotate, and the perimeters will charge. And for the triangle, again, there's an easy solution, which is an axis of symmetry. So to make things interesting, this convex shape shouldn't have an axis of symmetry. So here is one. This is hexagon, I guess. And again, we want to cut this into 2 pieces of equal area and equal perimeter. And one way to do that is that you say we take a vertical line, which cuts this into 2 pieces of equal area. That you can always do. And then we rotate this line, and we rotate it in such a way that we always have the same area on the right side and on the left side. And if we do this, then we are sort of in a circle. So the configuration space is a circle. And we always record what's the perimeter on the right side and what's the perimeter of the left side. So that's the point where we move from a problem in discrete geometry in the plane, really to a topology problem, because we have just discovered that the configuration space of partitions of a polygon or a shape into 2 parts of 2 convex parts of equal area, it's really a circle, because it's only the angle in which you have the line which determines where you are. And if you rotate by 180 degrees, again, you have a vertical line. So that's why the circle closes up. And now we use a theorem from either from analysis or from topology, as you like it, the intermediate value theorem, which says if we rotate the line, and if in the beginning the perimeter was larger on the right side than on the left side, and then we continuously move until 180 degrees where left side and right side have interchanged, then it suddenly means that on the left side it's larger than on the right side. So if the difference was positive in the beginning, it's negative in the end, and since everything is continuous, it has to be zero in between. So this means we've used continuous, we have basically used topology, and we've used continuous functions, so we've used analysis. And we've solved the problem for n equals 2 and any shape. That's definitely a good start. Now, n equals 3, we try and partition into 3 parts. It turns out that this is much harder. We would be looking at a partition like this, which perhaps would be 3 shapes of same area and same perimeter, which is still easy to find in this case because the triangle has an axis of symmetry. In general, it's not at all clear why a solution should be there. And in the end, this means that since you don't really get that far with just trying out examples, you need a method. We go for methods, and they turn out to come from a completely different field, namely topology, where we look at configuration spaces. So you want to look at all the ways to cut a convex shape into 3 pieces of equal area, convex pieces, and that would be the configuration space. So if we cut into 2 pieces, then cutting into 2 convex pieces always means cutting by a line. And the equal area partition is determined by the angle. And so since you have only the angle, it means the configuration space is a circle. But for 3 pieces, what does the configuration space look like? We will get very concrete pictures later in the lecture. But in the moment, this is not clear. And if you look for equal area partitions into n pieces, it's even less clear. However, it turns out that there comes a method that comes again from a completely different area of mathematics, namely from optimal transport. Now, what is optimal transport? It's a theory that was started by an engineer called Gaspar Monge in 1781, so it's a very old theory, and the main theorem that we need there is by an economist called Leonid Kantorovich, who it happens got a Nobel Prize in economics in 1974. So we have the first Nobel Prize winner in our lecture because we need one of his theorems. Nobel Prize in 1974. The theorem is really from 1930, so 44 years earlier when he was a much younger man. Today, if you want to know what optimal transport is about and what tools are available, then you look at this book by Cédric Villani, Fields Medal winner from 2010, a French mathematician, a very colorful one, exciting one. And so we learn optimal transport and we fix a theorem that we can use for the following. What does the theorem say? It says the following. So this is Kantorovich's theorem in a modern version. It says if you take any n distinct points in the plane, think of n equals 3, and an arbitrary polygon, think of our hexagon, then the weighted Voronoi diagram partitions the polygon into n pieces of the same area. Now that's the theorem. It comes with ways to calculate also all these things, but what does it mean? Well, in the end for us, it means that the configuration space of n points in the plane, and that's a very classical topological space, parameterizes weighted Voronoi partitions into n convex pieces. So that's what we can use. Yeah.
Excuse me, Professor Ziegler. One curious question in this particular regard is that we know about affine combination of certain points in an affine plane in order to find the barycenter.
Yeah.
So whether that kind of technique did not work in this particular case, if one can think of, for instance, 6 points which are forming the polygon in an affine plane, affine point space, and then apply the technique of using the barycenter. So barycenter will come up with all the points which are inside it. So this kind of theorem works in the same way.
Yes, and so the barycenter is one important component in there, and for our problem, it just doesn't give us enough data. So what barycenter basically means that if you have n points in the plane, you can move them in such a way that the barycenter of the points is the origin. And that sort of normalizes our configuration space. But it just moves it. It doesn't make it less complicated. So I will illustrate what this configuration space is. It turns out to be a reasonably complicated space that we have to understand. And the barycenter in the end, it's just one point and doesn't give us enough data. We need much more. But it's basically, it's a starting point. It's the first thing we have.
Thank you. Thank you.
So here is pictures again, starting with the triangle. So this theorem says the following, that if you have 3 points and we take them in the triangle, 3 points in the plane, then there is a Voronoi diagram, which basically for each point says what's the orange part that's closer to this point than to all the others. And weighted Voronoi diagram means that you give the points weight, and if a point has a large weight, then it will get a larger region than if it has a small weight. So these weighted Voronoi diagrams are a very important structure. And here it means that if you adapt the weights for any 3 points, then with the adapted weights, you get the Voronoi diagram as drawn here, in such a way that the areas of these 3 parts will be equal. Now it gets more interesting if we take different points. So for example, if you take these points, then the weighted Voronoi diagram, which gives you equal areas, might look like this. And that might also be the solution for our problem with the perimeters. But in the moment, this optimal transport theorem, which is a deep theorem, only tells us how to get the weight so we get equal area. Now, just to illustrate that this is current stuff, optimal transport is used for many different things. So for example, it is used for agriculture to redistribute fields in the countryside. This is a cover of the Mathematical Intelligencer from 2014. Work by Peter Gritzmann in Munich, Germany, illustrated there. And in this paper, he illustrates how useful weighted Voronoi diagrams and optimal transport are in agriculture. So in that sense, the type of mathematics that we are using is really practical. Of course, one thing I should stress is that people always try and divide mathematics into different fields. And in the end, we shouldn't do that and it shouldn't work. So people talk about pure mathematics and they talk applied mathematics. And already from this part of optimal transport, one sees that this is the same mathematics. There's also recreational mathematics, which basically is all the math that you have fun with doing it. And so again, this should be the same mathematics. And there's what people call computer science. And again, that's a part of mathematics that is very useful and in parts very theoretical. there's operations research. That's where this optimal transport thing comes from original. So it's a part of economics if you want, but actually this is very good and very useful and very interesting and very recreational mathematics. So again, one shouldn't divide things. All we do here is mathematics, and that's good. We also do some applications of mathematics outside or in mathematics. So this redistributing fields in the countryside, of course, is applications of mathematics. What my lecture is about more is that there's good theories, but there's also good problems. And a good problem is one that leads to something, and good theories are ones that you can use to solve problems. At least that's my criterion for that for the moment. So let's not divide mathematics too much into different things. It all belongs together. Anyway, we had looked at this problem, and the problem says you're given a polygon, you're given a number n, and number could be 3 or larger. Can you divide this polygon into n convex pieces of the same area and same perimeter? And this optimal transport stuff tells us easy ways to divide into pieces of equal area. But actually that's something that you could have done yourself also, because you can divide into equal area just by vertical lines. So it's not really needed to use optimal transport, but we will need that now. And the next thing we need will be versions of topology, and actually versions of the Borsuk-Ulam theorem. And this is my favorite book in the area by Jirka Matuszek from Prague, called Using the Borsuk-Ulam Theorem, Lectures on Topological Methods in Combinatorics and Geometry. So this is my favorite topology book, perhaps. It's wonderful. Some people call this complicated mathematics because topology is a very complicated part of mathematics. But actually other people sell this as child's play. So if you look at this eBay advertisement, then you find this book here in eBay in a category called books, and subcategory children and youth literature, subcategory fun and games, subcategory knowledge for children. So the Borsuk-Ulam theorem is clearly knowledge for children. Go for it. Anyway, it's a deep theorem from topology. For our purposes, it's still not good enough. What we will need for our theorem and for our problem is something called Equivariant Obstruction Theory. And the good way to learn that theory is to look it up in a topology book by Tammo Tom Dieck, a mathematician from Göttingen, Germany. In his book called Transformation Groups, there's chapter 2 on Equivariant Obstruction Theory. A very good treatment, but unfortunately one that's rather typical for topology books, without any pictures, just with diagrams and explanations. So it's hard work to get in there. And actually here, I said chapter 2, it's chapter 3. In chapter 3, there's this theorem, chapter 3.10, which tells us something complicated from algebraic topology that we will make useful for our little problem about partitioning a polygon. And I will not go into details of this now, but we will illustrate on our problem what's really happening there. So here's the details. For our problem, we try and understand the following. We have EAP of n would be the space of all ways to cut our polygon into n convex parts of equal area. And actually, we do not understand this space very well. But in the end, we want to say that one of these ways to cut it will also have equal perimeters on these n pieces. And so this is a configuration space. It's not well understood. There's a paper by Emerson Leon, my former PhD student, and myself, where we try and analyze this space. It's complicated. This S of Wn turns out to be a space that we understand very well. It's a sphere, and it will be represented as all the points in R to the n, where the sum of the coordinates is 0, and the sum of the squares is 1. So this R to the n is an n-dimensional space. If you put all the sum of all coordinates equals 0, that's an n-1 dimensional space. And it's an n-1 dimensional hyperplane. And if you take sum of the squares equals 1, then that's the n-2 dimensional unit sphere in this space. And what's the map? Well, the map takes these n pieces and maps to n values, and the n values will be the n perimeters minus the average, and that's where we take the barycenter and move the barycenter to the origin. So that's what Imran Anwar had asked for, and then we normalize. Namely, the situation we look at is the situation where there's no solution where all perimeters are equal, which means if you subtract the average, then the perimeters minus the average will not all be 0. And if they're not all 0, then you can also divide by the sum of squares and get sum of squares equals 1. And now it turns out that this is not only a continuous map between topological spaces, but it's equivariant. Namely, if you permute the pieces of your partition, then you permute the perimeters of their pieces, and also after you average and normalize, you still permute. So this is not only a continuous map, but it's an equivariant continuous map where the permutation group will permute the pieces and will permute the values. And so we are in the area of continuous equivariant maps, and this is in the middle of algebraic topology. And what we are in the process of setting up here is a configuration test map scheme for this problem, and that's a very general type of scheme that Zakaria has formalized in an Indian mathematician, and the place to read about it really is Matuszek's book, the Child's Play book from 2003. Now,
excuse
yeah.
me.
Yeah.
What is this structure EAPPN? This is configuration, special kind of configuration you are using here?
Yeah, so it's EAP is for equal area partitions.
Equally.
Right? So P would be our polygon, and EAP is the partitions into n pieces of equal area. Right, and that would be a space that we do not really well understand, but it's in there. It's a topological space. One can show that it's compact. There's a few things one can say.
Okay. Thank you.
Yeah. Now, since we don't understand the space, you ask about it, but we don't really understand it. We use a different space. And the different space that we use is this very classical configuration space. It's just the space of endpoints in the plane. No two of them are equal. And endpoints in the plane, of course, you can, since they are labeled, you can write this as all the 2 by n matrices where no two columns are equal. And this is a very beautiful space. It's, if you want, a 2n-dimensional vector space, but with n-choose 2 subspaces removed. And it turns out that this space has been studied by many different people over the decades. And a very early paper is by Fox and Neubert from 1962. There's, for example, a paper by Sundaram and Welker from 1997. Imran and I had just talked about Volkmar Welker from Marburg. That's his paper. So there's papers also by Pavle Blagojevic, is my co-author, who's also here somewhere on the screen. So many people have worked on understanding this space, and I would say this is a very well understood space by now. And this type of space, the complement of a arrangement of subspaces, this can be studied. Now we have this beautiful map from the space of endpoints in the plane to the space of equal area partitions. And this is this optimal transport map, which where the main part of constructing this map is really in Kantorovic's paper from 1938. That's the economics Nobel Prize winner. And again, this is an equivariant map where if you permute points in the configuration space, you get permuted pieces of these partitions. And the ansatz to use this here, you find in a paper that was finally published 2013 by Karasov, Hubbard, and Aronoff. For this game we are playing here, take endpoints and take the weighted Voronoi diagram. Now, the next piece that we will need is that this configuration space of endpoints in the plane is still too complicated for us because it's not compact. It's not a cell complex. And to use this stuff by Equivariant Obstruction Theory by Tom Deek, we will need a cell complex. So we will need a finite cell complex that we can use sitting inside this configuration space in order to construct maps or to show that they are not exist, and they don't exist. And it turns out that this regular cell complex in this configuration space is a really beautiful thing with lots of combinatorics, and I will show you this in an example how it looks like. It's really beautiful combinatorics, and something that I guess in some sense perhaps was known, but we worked it out explicitly because we needed it explicitly. Okay, so that's the cell complex model that you can trace back to Fox and Neuwirth, but Pavle Blagojevic and I worked it out for our paper.
May I have a question?
Yes.
I don't know. So in this, at the top, you use this symmetric group Sn.
Yeah.
So is there a way that we can change it with the braid group like Bn? Is there a possibility?
Yeah. So the braid group is always sitting in there, also because the colored braid group is the fundamental group of this configuration space, and so it's very important in this context also to understand this configuration space. For these equivariant maps I'm writing down here, it's very important that the group we are working with is finite. And so I'm very happy that in this case I can work with the symmetric group and not the braid group, because we really want to work with a finite group. And here we have all these n factorials sitting in there, and these n factorials come from the symmetric group acting here. And of course the braid group is not finite, and it's that creates other kinds of complications.
Okay, thank you.
Sure, thanks.
Thank you.
So here we are. Now, again, so what I'm showing you is this game of equivariant maps. The cell complex with this curly f is just a subset, if we want, of this configuration space. So constructing this map is easy. Now, here's the summary of what we've done. So there are a few things that I only sketched to you. It says the following: if for some n, so think of n equals 3, and for some polygon, there is no solution to our problem. So if there's no equal area partition into n parts with equal parameters, Then there is an equivariant map from this little cell complex F2n to the sphere, which is equivariant with respect to the symmetric group. And this means we've really reduced everything to a calculation in algebraic topology. And so one message from algebraic topology is that continuous maps in topology always exist because you can map everything to a point. But equivariant maps in general do not exist. And that's the beauty of the Borsig-Ulam theorem, which is sort of the first example of equivariant maps that don't exist.
May I ask a question at this end?
Yeah.
Okay, Professor Ziegler, you know about the famous construction problems from the Greeks' time, the construction of the angle, that we can't trisect the angle every time.
Of course, yeah.
Okay, if I think of this particular problem, okay, one approach is there, what you have explained. And if we think of having a center of the polygon, and then all the partitions will relate with the angle, the way the points are moving, the way you started in the beginning.
Mm-hmm.
And the same problem can be translated into the, ultimately comes down to the construction of the angle, the way it is being done in that particular context, the construction of the angles.
Yeah.
And that particular approach can be another way of answering these kind of questions.
Yeah.
I was just curious about the way you beginning. I was thinking about probably you are going to connect that thing with this particular question.
But that's a very good question. So let's go back to our problem. We have this polygon we want to cut into n pieces of equal area and equal partition, equal perimeter. In some sense, this is 2n conditions, or 2n minus 2, right? Because I want these pieces to have equal area.
Yeah.
So that's n conditions, although if n minus 1 pieces have the right area, then the last one has also. And then also you want to have equal perimeters, that's also n minus 1 conditions. So in the end, we have 2n minus 2 conditions. However, if you look only at partitions which choose a point, say the barycenter or a different one, and then the angles, then you have n plus 2 free parameters, right? Because 2 for choosing the barycenter or any other point, and then n different angles. And basically, you can use these angles to get the areas right, if you're lucky, or if the barycenter does it. But there's not enough parameters to get the perimeters right. And that's why we have to do things that are more complicated here.
Okay, now I got it. Otherwise, I was thinking about the same problem can be translated into the construction of the angle, the way it is being done for dissecting an angle.
Yeah. But it turns out that this problem is so complicated, this Nandakumar Ramana Rao problem, exactly because you need all three parameters. And this 2n minus 2, in the end, is also the dimension of the configuration space. And there's not much freedom in the problem in the end.
Thank you.
Okay. The other observation is that we have now translated our problem into a topological problem where we want to show that something is not possible. And it turns out that in many pieces of topology, that's what topology is good at, is to show that certain things are not possible. And that's what we do here. So here we want to show that this equivariant map from this cell complex in the configuration space to the sphere does not exist. And equivariant obstruction theory is the tool that can be used to decide whether equivariant maps between cell complexes exist or not. And that's Tom Deek's book. Okay. Now here's the special case for n equals 3. And I want to illustrate to you how to solve this problem for n equals 3 for this special case. And I do this because I can do this really very explicitly and very geometrically. And that's where the picture show comes in. Now, here on the top of the line, you have F23 to be mapped to SW3. Now, SW3 is really, so we're in the case n equals 3. We want to cut into 3 different pieces of equal area, equal perimeter. Now, SW3 is really just a circle. And what is F23? Well, F23 is a 2-dimensional cell complex, which looks like the graph I have here on the left. And this is a graph which has n factorial, which is 3 factorial, which is 6 vertices. And it has 12 edges, which I have also drawn here for you. And so this is a cell complex. So the edges you can really think of as physical strings. And then the cell complex is 2-dimensional, and which means it also has 6 hexagons. And these 6 hexagons we glue in there. And there's a very complicated labeling for the cell complex where these hexagons are associated to permutations. And this is hexagon number 1. This is hexagon number 2. This is hexagon number 3, number 4, number 5, number 6. This is these 6 hexagons. And this together is the cell complex F23, consisting of 6 vertices, 12 edges, 6 hexagons. And now we want to move this cell, map this cell complex to the sphere. And the sphere is really this 1-dimensional circle. And to map the cell complex, well, to map this graph to the circle is easy. We can basically map like this, just around the circle. However, if I do that, then I cannot extend this to the full hexagon here, right? Because you cannot map the boundary of the hexagon to the circle and then extend to the interior of the hexagon, which means we have to modify the map. And that's what people do in obstruction theory. If I map this yellow circle like this, then I can extend to the to a map where also I map the interior of the hexagon to the circle. I hope that you can see that. However, now I've messed up things in a different way. Namely, the map is not equivariant anymore, because the group of 6-element permutation group acts on the cell complex on the left. So it also acts on the circle on the right by permuting these coordinates. And I'm asking whether there is an equivariant map. And equivariant means if you permute on the left side, you also permute on the right side. And that now means that if you modify your map, like I did, then you also have to modify all the corresponding pieces with the symmetry group, which means the map that I've drawn for you here is a possible way to map the yellow circle on the left to the yellow circle on the right. And so what we have to do in order to get this equivariant map is we have to modify the original map, namely this one, in such a way that it's equivariant, and in the end it can be extended to the interior of the hexagon. Now, the way you have it here, this is a graph problem in some sense, but what we really see is that we modify the map in such a way that in the end, on the right side, we get something of winding number 0. Because if it has winding number 0, you can extend to the interior. And if you work out the details, you find that this map up there exists if and only if there is a solution to a certain equation in integers. And the equation is 1, because my first attempt of the map was just to map it around the circle. And then always, if I modify an edge, I also have to modify two different edges. So it always comes in multiples of 3. And I can also modify on the other edge, but it also comes in groups of 3. And so in the end, the map exists if and only if there is a solution to this equation. Or in other words, the map does not exist if there is no solution to this equation. Now, you all stare at this, and does this equation have a solution in integers? Now I want to have an answer from one of you. Anyone? Yeah. So if I put
no, they can't be. I think so.
Why not?
Okay, if I take 3x2 on the other side, so the other side is divisible by 3, but the right-hand side would not be divisible by 3 then.
Yeah, exactly. In other words, the left-hand side is congruent to 1 mod 3, right?
Yeah.
And the right-hand side is congruent to 0 mod 3. That's the same argument.
Yeah, same argument.
So this means this equation doesn't have a solution, which means this map does not exist. And this implies that there's always a weighted Voronoi partition into 3 pieces of equal area and perimeter, which means we solved our problem for n equals 3. Now, of course, then we get going and we try and do the same thing for n equals 4. And it's the same game basically, except this configuration space or the cell complex F24 is much more complicated. We don't have a hexagon now, but a permutahedron, a 3-dimensional one, and a cell complex with 24 permutahedra and 24 vertices. So it's rather complicated, and we do not map to the 1 sphere, but to the 2 sphere. But it really is the same game, again, with modifying sort of in groups, where if you modify your map on this hexagon, then you also have to modify it in these 2 other hexagons. So that's the combinatorics of the permutahedron with these 4 hexagons that belong together. There's these 6 squares that belong together. There's the 4 other hexagons that belong together. And in the end, the game says that this map for n equals 4 up here exists if and only if there is a solution to this equation in integers, or in other words, it does not exist if there is no solution to this equation in integers. So question again, does this equation have a solution in integers? Anyone? Well, it's the same game as before, right? Right?
I think this time we will be having some.
Sorry, this time?
This time we will have.
No.
2 plus 0. No. This time again, no.
Yeah, it's again no, because the left-hand side is odd, right? And the right-hand side is even. So there's no solution, which means there's no map, which means there is always a weighted Voronoi partition into 4 parts of equal area and equal perimeter. And now, of course, we get greedy. If we can do it for 3 and for 4, then we do it for 5. And we realize what the pattern is. And what are these numbers? 1, 4, 6, 4. Well, it really looks like binomial coefficients, right?
Binomial coefficients, yes.
And indeed, what we prove is that this map for n does not exist if this equation in binomial coefficients does not have a solution. So which means we've reduced everything really to a number theory problem about divisibility of binomial coefficients, which I think is nice. So we've moved from discrete geometry to optimal transport to algebraic topology and equivariant maps, and now we are in number theory. That's where the queen comes in.
Okay.
So,
just a question. So all the maps, these maps are non-equivariant in the previous one.
Well, in these cases, we are looking for an equivariant on the cell complex on the left and the sphere on the right. And we've shown that there is no equivariant map for n equals 2 and for n equals 3.
Okay, so all these maps are non-equivariant.
Yeah, I mean, a non-equivariant map always exists because you can take the cell complex and just map everything to one point on the sphere. That's a continuous map. But so the n equals 2 situation, what we have on the left-hand side is a sphere, and on the right-hand side we also have a sphere, but that one has smaller dimension. And the Borsuk-Ulam theorem says that there is no equivariant map from the n sphere to the n-1 sphere. So that's the basic pattern of why equivariant maps don't exist. And that's basically the n equals 2 case. And we've now done n equals 3 and n equals 4. And we are just sort of storming ahead to do the rest. Now, I have to speed up a little, but that's where number theory comes in, which according to Gauss is the queen of the sciences. Well, he says mathematics is the queen of the sciences, and number theory is the queen of mathematics. And here is the theorem that we need from number theory, and it turns out we are also going back to India, a theorem by a guy called Balagram. In the first volume of the Madras Mathematical Journal, the first paper, so this is the Times of Ramanujan, and he shows that this equation that we are looking at has no solution in the integers. In other words, the nth row of Pascal's triangle has a common factor, if and only if n is a prime power, right? I mean, of course, I talk about the nth row of Pascal's triangle without the ones at the end, right? And so this equation has no solution if these binomial coefficients have a common factor. Otherwise, it has a solution. That's the Chinese remainder theorem. And so Balagram tells us that everything works if and only if n is a prime power. Now we look at the Pascal's triangle. And so this is an image from a book called The Number Devil by Hans Magnus Enzensberger, a German poet, and he wrote this children's book about the number devil. And there you find this young kid called Robert, who is sort of enticed into mathematics by the number devil, and the number devil shows him the binomial triangle, and this is it. And there's this one image where this line is highlighted. And so what we look at is whether the Pascal's triangle has a common factor. And here the common factor is 2. I don't know, can you see my mouse on the screen? So
yes, we can see that.
Yeah, so here's the common factor is 3. Here the common factor is 2, right? 4, 6, 4, it's all even numbers. Here the common factor is 5, but on this red row, there's no common factor to these numbers. And indeed, the equation does have a solution. For example, 1 minus 6 minus 15 plus 20 plus 0 equals 0. So it means for n equals 6, there is a solution to our equation, which means this equivariant map exists, which means our proof doesn't work. But for n equals 7, again, everything is divisible by 7. For n equals 8, everything is even. So it works if and only if there is a common factor. So here is the theorem that we have proved. And this refers to, there's a paper by Karasov, Hubbard, and Aronoff where they use different methods, and we believe also there's there's enough problems with these methods that one should do a second proof, and that's what we did. Pavle Blagojevich, and our paper was published in 2014, and we have proven, and I've sketched to you the proof. If n is a prime power, then every polygon admits a fair partition into n parts. And Nandakumar and Ramana Rao calls this fair if they have equal area and equal perimeter. And if n is not a prime power, then this is not wrong. This is not known to be wrong, but we know in this case that this map, this continuous equivariant map exists, which means you can solve the problem in the same way. And indeed, we've constructed a different type of theorem, which says that if n is a prime power, we can prove first something much more general. We say mu is a continuous measure on Rd, so this replaces our polygon. And you take d minus 1 different functions. This would be in the special case area and perimeter. And you only assume that these functions are continuous. And then there is a partition of every polygon or any measure into n convex pieces, such that these pieces have equal measure, and these additional functions take the same value on all pieces. So this is a vast generalization. And the neat thing is that if n is not a prime power, then this is completely wrong for all d, for all measures, and for suitable functions. So for example, it's wrong for d equals 2, for a square, and for suitable continuous functions that measure something and which are something different from perimeter. So this also means that there is these problems from discrete geometry, and this is one, which are true for prime power cases and wrong for other cases, which I think is surprising for discrete geometry problems of this type. Okay, this is also the end of my lecture, except I brought you a poem by Hans Magnus Enzensberger, who is the author of this children's book, The Number Devil, which I think has also been translated into 33 different languages, so you should be able to get it in your favorite language. This is a poem by Enzensberger, which I think doesn't even exist in English, so here it is. And it's a poem about shooting sparrows at cannons, where I will not read this to you in general, but I will just read the last line, which says, "Cannons at sparrows." No, the first line says that that he has made the mistake of shooting with sparrows at cannons, and the last line says that cannons against sparrows, that would be to lapse into the inverse error. So in mathematics, this is a shooting with big cannons at small problems, which is a lot of fun. That's what I wanted to show you. Sometimes we do the opposite thing. We shoot with sparrows at cannons, and then we don't get very far. All of that happens. So that's end of my lecture, end of my presentation.
Thank you very much, Professor Ziegler, for a wonderful talk. Any questions from the audience side? Yes, Professor. Yes, Nakib. Yes, Nakib.
So I have just remarked, it's a wonderful talk. I really enjoyed it. I think when you say that we can use sparrows to cannons, so I just reminded the Angry Birds app, which my son is very like to play.
Yeah. I wasted a lot of time on Angry Birds some years ago. I think this is shooting sparrows by cannons, right? That's what it is. That's still a different thing. Yeah.
Thank you very much for a very nice talk. Thank you. It's a pleasure to hear you.
Professor Ziegler, I'm a bit curious about to know when Monge used these theories. You mentioned Monge paper as well,
Yeah.
in the references. So and like cyclic Villani, so there are some application aspect. But what Monge was doing with these kind of thing? Anything?
Yeah. So I think this Monge was an engineer really, and the problems he looked at were really transportation problems in the following sense that so the quick thing would be you have something like endpoints in the plane and another endpoints in the plane, and you want to move these endpoints to the other endpoints. And if you want to minimize the distances where you have to carry stuff, then Monge tells you how to do that. And in Monge's theory, what people use is what's now called the Wasserstein distance, which is really distance squared. And that's where you get the beautiful theory. And there you can then generalize from endpoints to a measure and convex pieces and all these. But it's, I think the original problems were something like you have a huge pile of something and want to move that to, I don't know, a huge pile somewhere else or several piles. How do you do this most efficiently? And so it was very practical problems.
I was just curious because I don't think during his time the topology was developed by that much what you are using at this point.
Yeah, at the time, this was sort of, I think today we would do this rather combinatorial, actually. At that time, I think this was more or less, this was about measures and analysis and calculus problems. And, and again, the modern theory, I mean, Villani in his book, he's of course a high power analyst. And he says that this can, certain proof can be done also combinatorially, but this is very complicated, and gives a reference. And if you look at the reference, you see that the reference is very nice and it's very complicated and it's also very simple and it's also incorrect. Because in the original version of this reference, they were doing linear programming duality in the wrong way. So there's a corrected version of this paper that it's by a Berkeley professor explaining how you do this Monge theory by linear programming duality. And so you have to take the corrected version. But I found it nice that Villani says it's, it's complicated because it's combinatorics. And I would say it's easy because it's combinatorics, but that's how different people have different perspectives at what's a canon and what's a Sparrow.
And one last curious question is about the cell complexes you was using associated to the permutation. So I never came across those before. So this is a special kind of cell decomposition or cell complexes you are using there.
Yeah. So the
sorry.
Yeah. So the general theory you use there is the theory of CW complexes. In this case, this is regular CW complexes as you find them in topology books like the one by Munkris, which you really get by starting with vertices, then you glue in edges, and regular means you do not identify stuff on the boundary. And then you glue in cells, triangles, two-dimensional cells, and it's regular if you do not do identifications on the boundary, and so on. So it's very beautiful. And regular cell complexes are very combinatorial. If you can do barocentric subdivision, then you get simplicial complexes. And in our special case for these configuration spaces, the cells are really permutahedra. So you have vertices, edges, hexagons, three-dimensional permutahedra that you glue in. So it's very beautiful combinatorics for this particular example. But the general theory is regular CW complexes.
But the labeling is new for me. I am aware about the CW complex, but the labeling you was using and the direction you are using, that is something which is, this is also mentioned in Munkris?
No, and it's not improved from the book. I mean, we don't do topology there, or very little. We do the Borsig-Ulam theorem, but that's it.
Okay, Hania, over to you now. Hania.
Yeah, hi. Thank you so much for a wonderful talk. It reminds me of an article that I've read on with the same title, perhaps in Notices or somewhere else, but a while back. It's really it's really very it's quite remarkable the way these different pieces plug in together to give you some real answer to however small the question is, but just different. So I just want to go back to the scheme of things and just to confirm if I'm getting it right. So when you talk about this configuration space test map scheme, so you basically started out with this this space that you defined to be equal area partitions of your polygon into n pieces, and this map, equivariant map from this space to this S of Wn, which is a sphere. And so how do you get to this regular cell complex? So my question is really, I mean, how do you think of this? To get to this, what's the idea? As in, how do you come about with this regular cell complex? And then, where exactly do you use DX obstruction theory to say that, if this, what makes it a test map scheme, basically?
Okay, so the reason how you, the way you find these cell complexes is the following. First, I mean, we arrive at this configuration space of n points in the plane, which is much easier than the partitions. And that's a classical space, and it's a complement of an arrangement of subspaces. In this case, this is subspaces of dimension 2, of codimension 2. And it turns out that there has been a lot of work on understanding the complements of subspace arrangements and to build cell complexes that really carry the topology of that. And so what I've shown you, the cell complex with these hexagons and permutahedra also, is really the concrete special case of these rather general constructions. And these general constructions, they go back to these pioneers of knot theory, Fox and Neuwirth and so on, where they constructed these cell complexes really also to understand the braid group and these things. I think our discovery was that in this special case, this really very beautiful combinatorics comes out. And second part of your question, equivariant obstruction theory, I've somehow tried to put this into words, where equivariant obstruction theory really says the following, that if you want to construct equivariant maps, then you do this sort of skeleton by skeleton. You first map the vertices, and then you map the edges, and then you map the two cells and so on. And if at some point you get stuck, if you cannot, I don't know, glue in the two cells, then you have to modify in the previous dimension. And the question whether you can modify in the previous dimension in the end leads to these integer equations. And in general equivariant obstruction theory, this leads to the question whether a certain cohomology class is zero. And this is very geometric in the end. And this is this equivariant cohomology class, which really just measures the stuff that I have shown you in the pictures. So this is one way where one can make this equivariant cohomology very, very explicit and very geometric. And in general, it's much harder to make this so concrete, but it really is the same story. And these integer equations in the end is the equations which say that to take a certain equivariant obstruction class, and whether this class is zero, and it's zero if it's a co-boundary. And what you have on the left-hand side is exactly the co-boundary computation for the specific cell complex. So that's the story. So it's one situation that I love a lot, because there you can make this this really, I don't know, dry and abstract equivariant obstruction theory very concrete and very geometric. I think it would be nice to work this out in such a way also in other situations. But that's the nicest one I know.
Thank you.
Thank you very much.
Any other question or comments from the audience? If this is the case, let us thank Professor Ziegler once again. Thank you very much for accepting our invitation and for a wonderful talk. And one more announcement for the audience who are interested to obtain the recording of this talk. They can write to us at mathevents@lums.edu.pk. We can send you the recording in reply to that email. And we are not going to place the recording of this email in any open source. So it will be on request. It can be sent to you on request. That's all.
For your eyes only.
Yes, we are going to have. Yes, Professor Ziegler. Thank you, everyone. Would you like to say something?
Oh, let me just say thank you for welcoming me. Thank you for setting up this wonderful format, and I'm very happy if I can present our mathematics in such a way. And if there's more questions, send me an email. I'm reachable on email. Use the math email, not the president's email, which reaches me more directly.
Thank you, everyone. Thank you. And this is wonderful talk. Thank you, Professor Ziegler.
Thank you to all of you. Bye-bye. Have a good time and stay safe in these difficult times.
Accept our greetings for the Easter.
Thank
Have
you.
a wonderful, cheerful
Bye-bye.
Easter. Bye-bye.
Yeah.